Well, welcome to Aviation Weather at WVU Tech here. Uh, I figure every couple of weeks I'm going to try to do one of these. We'll see how you like it. I've done it before and had some comments that liked it, and some people didn't. But I'll try to use it to try to add to what you're learning in the book, what you're learning through the labs, and maybe even help you with some of the labs and eventually the test as well as you go through here. So let's start with the atmosphere. We're going to start with the composition. One of the things that I want to stress here, the first 6 weeks or so of the course, you're going to learn a lot of the basics of the atmosphere. Why is that important? Because everything else from that builds on those basics. You have lots of hazards in weather for aviation. But if you don't understand the fundamentals, at least some of the fundamentals behind the weather, you can't really understand what those hazards and how to deal with them and what they actually mean. So this is where I'm going to start talking. We're going to do the basics first, and then we'll move into the hazards. But we'll probably pick up a few hazards along the way anyways, things of interest. So we're going to start with atmospheric composition. You can look here. There are two of the biggest gases in the atmosphere are oxygen and nitrogen. So with that in mind, their proportions never change. In other words, the same percentage of oxygen and the same percentage of nitrogen are here at the surface or here when you're flying a plane at 34,000 feet. However, the atmosphere thins out as you go up. It spreads out, gets less and less molecules in it. So what does that mean? Well, while you have the same percentage of oxygen, the amount of oxygen available is going to become significantly less the higher you go up in the atmosphere. So the percentage is the same, but the amount changes. So that's just something you need to know and understand. Basically, as a pilot, the higher you fly, the less oxygen you have. Well, if you climb Mount Everest or Mount Denali in Alaska, like this one shows, that's something you need to be aware of. Water vapor is a variable gas in the atmosphere. Did you know that? That you see all those clouds out there? It changes. The amount of water vapor literally changes hourly to daily within the atmosphere. And it can only gas in the atmosphere that exists in all three states of matter. It's a gas, it becomes a liquid, and it becomes a solid. So water is really something we're going to discuss a lot as we go through this course. So looking through here a little bit, we can go down through here a little bit with one of the properties of the atmosphere is that temperature, density, and pressure are all related, called the ideal gas law. We're not going to show you a lot of math questions or anything like that, but we need to know a little bit about how things relate, and it's easiest to see that when you look at them in a mathematical equation. So pressure, the pressure of the air wherever you are, is going to equal a constant times density times temperature. We're going to go into more detail on what each of these things are. Temperature you might be kind of aware of out there, but we're going to talk about temperature. We're going to talk about density, and we're going to talk about pressure. But just know that if you know any two of them, you know the third. And when you look at a weather map, you always will know two of them. So it's something to know for your beginning to get into this coursework here a little bit. So you have what's called a density altitude as you're flying. Say you landed in Phoenix and it was a very hot day. Temperature is well over 100 degrees, kind of like right now. What does that mean to density? Well, first thing it does, we just said pressure is related to density and temperature. Well, if the temperature is, say your pressure is the same, and the temperature is 100 degrees, so it's high, that means your density had to come down. So at the same pressure, the higher the temperature, the lower the density. Same thing happens in wintertime. You get some very, very cold air masses in Fairbanks, for example, or anywhere in a lot of the U.S. in the wintertime. What happens to that density? Well, the density has to go up. Pressure stayed the same, didn't it? We're going to say. make the assumption. So the temperature went way down, so the density had to go up. So you can see right here how they're all related to each other. So looking at that, one other thing I wanted to show you, thinking about the atmosphere, pressure really decreases in altitude in the first little bit of the atmosphere. And then it takes a lot less to decrease. So if you were to look at half the atmosphere is considered about pressure, we're going to measure in 500 millibar increments. So 500 millibars will be the pressure. So 500 millibars is about halfway through the atmosphere. Halfway through the atmosphere, you're up at about, maybe about 6 kilometers up, about 18,000 feet up. Not real high when you're flying a lot of times, but half the atmosphere is already below you. So all that distance you go up further, you can see how that changes. So now that we've talked a little bit about this, I wanted to bring in just something else a little bit. The atmosphere is made up of different layers. When we talk about all the weather, almost all the weather happens in the troposphere. And all these layers are divided by temperature. Basically, the troposphere temperature, on average, is going to cool. This is a skew-T. You don't need to know that much about it right now, but we'll be going through it more and more as with time. A skew-T, it says skew with T, temperature is skewed to the right. You can see it right here. That is 0 degrees Celsius, and you can see the line that goes like that. Pressure is on the left, and you can see that, 850 is closer to 1,000. It kind of is a distribution that's very similar to the atmosphere. That, it's further between 500 and 300 than it is between 7 and 500 in the atmosphere. So you can see the atmosphere, the distribution is kind of similar to what the atmosphere would be like. So let's take the temperature. Red line is temperature. Temperature is cool at the surface here. It's way over here, and then goes to the right, so it actually warms a little bit in the low level here. But this is all within a couple hundred feet of the ground, and this is at night. We'll talk about some reasons for that. But then look at it. Temperature continues to cool after that until right here, almost 12 kilometers up. What happens then? Temperature kind of becomes constant and then really sharply rises. Right here is the tropopause. This is the atmosphere changing from the troposphere into the stratosphere. So there's something you've just seen real time in an observational setting. That altitude, the troposphere, is different. Say I were to take a point up in Minnesota at the same time, you could argue the troposphere is down at, tropopause might begin around 9 kilometers. So it would be lower. And that is going to be generally the case. The tropopause will be lower the further north you are in the U.S., the higher the further south you are. And when you get down to the equator, it'll be the highest. You get up to the poles, it'll be the lowest. And we'll talk about why that is as well as we go through here. So this is just all related to what you've now learned, a little bit of the basics about the structure of the atmosphere. So now we're going to deal with one element, and one element only, as we're talking about the next set of the atmosphere. So what is that element? It's energy, temperature. So where in the world does all this energy comes from that makes up the atmosphere? All of our energy that drives our atmosphere, that makes our weather, comes from the sun. So if the sun hit the atmosphere exactly the same way every day, weather would be a whole lot easier to predict. It does not. So with that, let's take a look at that a minute here. So the sun moves around. Here's June. Notice the rotation angle the Earth has right here. Here's the sun. Sun doesn't change. As the Earth moves, notice where this line is. Here's the equinox. Notice the line hasn't changed, but the sun, instead of hitting towards the North Pole is actually just kind of hitting in the middle now. Directly, the most direct sunlight. Oh yeah, then in the wintertime, it's kind of angling towards the south. That's because as the Earth rotates around it, this axis rotates as well. Doesn't change structure, it just rotates, and you can actually see how it changes with seasons. So in the summertime, like right now, the sun's very much in the northern hemisphere and angling in towards where we are right up here. So we're going to have more solar energy in the northern hemisphere right now. Matter of fact, there's light up at the North Pole almost all the time right now. So what does that mean? It gets a lot more heating up there than it normally does. So all of that plays a role in how the weather works. Because now you can see, instead of all this energy coming directly in at the same spot all the time, so that the equator would always be the hottest spot. No, it's not. In the summertime, it's warmer in the northern hemisphere. In the wintertime, it's warmer in the southern hemisphere. And right at the equinox, it's going to be equal in the north and south hemispheres at that time. So now that we've talked a little bit about that distribution of energy, let's move on to more about it. There's something, that energy is radiation. Just like a microwave heats up water in your microwave, that kind of radiation is what's coming from the sun. Radiation, if you think about it, is just a wave of energy, just like an ocean wave. And I kind of use ocean waves as a lot to compare them to. So if you have an ocean wave, say that ocean wave is really, really up and high, hits you very hard. That's one, from the time it lowest point to the time it reaches the next lowest point is a wavelength. So that is something you need to know for this course. One wavelength equals that distance. Say those waves were coming really frequently, just rocking your boat you were on or hitting you one after the other. They're going to be very close together. Because the speed of the waves are all the same in the electromagnetic spectrum, if you know the frequency of the waves and you know the speed, you can actually calculate wavelength, or vice versa, you can know the wavelength and know the speed. And the visible light spectrum, with that in mind, has the longest waves, and any longer waves are called infrared waves. You can't see them. While on the other end, the shortest is blue, and if you're shorter than that, they're ultraviolet. So now you can see that we have a spectrum of wavelengths, and the sun does do that. However, because we know the sun's temperature, we know approximately how much energy is coming from the sun, because every object radiates. Even you radiate energy out. And if you think about it, in the summertime, if you touch a hot black metal object, man, you can burn your hand on it. That's energy being radiated out from there. So now that we know a little bit about that, let's just take a look at how it comes down to the Earth. Radiation energy comes in, very first thing it does, it hits the atmosphere. Some of that energy is scattered, about 6%. What does that mean? Well, instead of going directly down towards the Earth, some of it rotates, goes back into space. Some of it might come down towards the Earth. Some of it goes at it like a parallel angle. It just goes in all different angles. Then you come down to clouds. It hits a cloud. Some of it's going to be reflected back into space. And then, at the same time, some of it's going to get absorbed by that cloud, and eventually some of that will go back up into space, and some of it will go back towards Earth. Oh yeah, the Earth overall reflects energy, but about 51% of the energy from the sun makes it to the ground and is absorbed by our Earth. So all these things go together. Reflection is an albedo, for example. Say you have snow, think about it. You need to put sunglasses on to look outside when you're out in snow after it's snowed. And why is that? Because the reflection, albedo, is all that energy is being radiated back into space by the snow. When the energy from the sun hits the snow, it gets reflected right back into space. So instead of 51% being absorbed, only about 10% is being absorbed. So depending on what kind of surface will depend again on how much of this energy is actually being absorbed. A black asphalt runway, a lot more energy is being absorbed than if it was a snow-covered runway. So it would be a lot hotter on the runway than it might be next to a pond or something. So now that you've known a little bit about how that energy is coming in and working, it gets a whole lot more complicated. And we're not even going to try to talk about all this, but this is just an example of the energy coming in and what happens. So there are three main ways this energy can move about now that it's got into the atmosphere. One is conduction. Think about touching your hand on a very hot object or a very cold object. That's conduction. The molecules from that object and your hand are actually transferring motion energy through that touch. Doesn't happen a lot in the atmosphere, but it does happen near the surface of the ground. And it happens to your planes, probably from the gases around them or from ice that gets on them or whatever. So you can see that it does occur. That's conduction. There's another process called convection. What's that? If you ever watch water boil and you see these bubbles going up, that's convection. In the atmosphere, there are air bubbles that go up and come down, and they move heat upwards and downwards through the atmosphere. That is the convection. It's a way of moving warm air upwards or a way of bringing cold air back to the ground. Advection. Advection right here, we're going to look at just a little tiny area here. This dashed lines are temperature lines. And the wind barbs, which you're going to learn more about, are all pointing perpendicular at 90-degree angles to these temperature lines. What happens then? Well, say you were on the Arkansas border here. This air, this colder air to the west is being advected, pulled in your direction. Oh yeah, say I was up here in the northern part of Missouri. South winds pulling the warm air northward to me. So think about it. In the U.S., where's the cold air going to come from? It's coming from Canada. Where's the warm air going to come from? The Gulf of Mexico, southern United States. So if you have a wind that has that kind of component, the chances are you're going to be getting that kind of advection. So if you have south winds, you're probably going to be getting warm advection. If you have west winds or northwest winds, you'll probably be getting cold advection. But by looking at a weather map and looking where the temperatures are and looking where the actual winds are, you can see something of this. So let's take a look. So all this now, we got to distribute all this temperatures around the globe. All this heat energy is distributed. So what that basically means is that somehow all that hot air that's coming, all that solar energy that's coming to the equator has got to move north. The atmosphere doesn't like to have a different temperature anywhere. It wants the same temperature everywhere. So it's always going to try to balance the temperatures. That's why we have storms. That's why we have the weather we have. So temperature is always going to be trying to balance itself. So the atmosphere is always going to be working towards bringing, wherever it's too hot, it's going to try to bring cold air. So it would, in basic terms of the atmosphere, it's trying to pull the colder air from Canada southward. By the same token, it's cold up north. Well, it's going to want to bring the warm air from the equator up to the north to balance itself out. So if we had no rotation of the Earth, nothing really happening of any consequence except heating the sun, you would have rotation coming, cold air rooming up from the north down towards the south, and warm air coming from the south to the north. So with that, I wanted to just show you a little bit of what, looking at some weather maps. And here is the current weather map for today. You're going to get into what these symbols mean. But basically, temperature is always going to be the upper left-hand corner of what we're going to call a station plot. Here's a station plot. So right here you have 82 degrees. This station, probably Omaha, Nebraska, my guess was thinking. So it's 82 there. Oh, what's it up here? 80 degrees up here in North Dakota. Look at this. It's 59 degrees up here in extreme northern North Dakota. If you were along this direction, you are having cold advection. Same thing here, you're having warm advection. So now you can actually see on a weather map cold and warm advection. With that as well, we've talked about the soundings and all here a little bit. Where'd they go? Let me bring up something here for you a minute I wanted to show you as well. And I can only look at it over here. So we'll bring it up on this screen real quickly. And here's the CONUS. We're going to look at the Great Lakes. And we're looking at satellite image. What is satellite? Satellite is just a picture of the clouds. In this case, by looking at satellite, you can learn a lot of stuff. For example, see these bubbly type of clouds here? These are all thunderstorms that are moving southeast out of Illinois, Indiana. Here's some more showers here, some more bubbles, little ones, a lot of cumulus clouds, some thunderstorms up over the western part of Maryland. But watch how the clouds move. Notice the rotation of the clouds here. So somewhere in the atmosphere, there's probably a low. Lows rotate counterclockwise. So this is a low pressure system. But there's all kinds of views of clouds. This one is called a geocolor. Basically, it's a true color day and IR at night. So say I wanted to look at the visible, just pure visible. If you were up in space, this is what you would see. You can see similar, looks kind of similar. But I look at something else, infrared. Infrared, we talked about radiation, and it can show you the temperatures of the cloud tops. And here's the temperatures marked. So these cloud tops are below minus 59 degrees Celsius, or even colder. So you can see some of the coldest cloud tops are right here in the southwestern part of Indiana. So if you're flying a plane, I don't think you want to go through those cloud tops. They're pretty high up. You probably want to deviate to the north around the northern edge, but you can see them actually growing and hence getting bigger all the time, and even some new ones forming out ahead of it. So maybe air traffic control might try to route you around these clouds. One other thing I wanted to show you is you can actually look at water vapor in the atmosphere. And this is a look at the water vapor in the mid-levels of the atmosphere. The greener it is, the more the water vapor is there, and you can see there's more water vapor along the thunderstorms and all. But one of the things I wanted to show you is look at how dry it is over in this part of the world right here. Lots of moisture in the eastern part, thunderstorms here, but there's very dry air right over this part of the area right now. That's why the thunderstorms aren't developing there. So hope you got a little bit out of what you've been looking at here. I just wanted to give you a taste this week. And one of the things, too, you're going to be doing, and I did show you this for a minute, is I want to show you just looking at weather maps. You're going to be doing an analysis of isobars. Isobars are just pressure, constant pressure. So here is an analysis of a 1026 millibar high. This means this isobar right here is 1024 millibars. So it just goes around. Everything inside of it is higher. Everything outside of it is lower than that pressure. Same would hold true with this line, 1020 millibars. Everything to the right of the line as you're moving along it would be higher. Everything to the left of the line would be lower. So when you're drawing these this week, that's how you're going to be drawing them. Just looking, basically connect the dots and try to find out where the dots might be. In some places, they're not exactly going to be at your station symbols. They're going to be between them. But it gives you something to look at. So I hope you get something from this. Let me know. I want to know if you have questions. or you just want to talk about things in the course or about weather. And I hope you get something out of it.